Last week we introduced a relationship between force and linear momentum. And this relationship or equation allowed us to relate force and motion to ultimately generate the equations of motion for our system. And that relationship said that the force acting upon point P is equal to the derivative of linear momentum. And we ultimately wrote that in the following form: F is equal to ma. This week, we are going to introduce another relationship we can use, and that is the relationship between torque and angular momentum. And same thing, that's going to allow us to relate force and motion information to, again, get out equations of motion for our system. And what this relationship states is that the torque of point P about point Q is equal to the derivative of angular momentum, which we indicate with an H. So the angular momentum of point P about point Q plus the velocity of point Q in frame A crossed with the linear momentum of point P in frame A. Now that we've defined the relationship between torque and angular momentum, let's actually define what these terms are. So in this equation here, velocity you should be very familiar with at this point. This term here is our linear momentum, which we introduced last week, and again that is equal to m times velocity. Next, let's introduce this angular momentum term. So the angular momentum of a particle at point P about point Q in frame A is the following. First, let's just review the notation. As I said before, we indicate angular momentum with H. It is a vector, so it has a bar underneath. We're taking the angular momentum of P about Q. So this is new, but that's what that slash means. And again, this is in frame A. And this is equal to RQP crossed with the linear momentum of point P. And so this we can then write out as RQP crossed with M, and then as I've written above here, right up here, I have M times velocity. And so just to draw that out, right? So imagine we have our reference frame here. So this is a fixed frame, so we have A1 and A2, say about some point O. And here we have a point Q here, and then we have a particle here. So the angular momentum is equal to this position vector here, RQP, times the linear momentum, which is equal to the mass of this particle, so we'll say it's m, times the velocity vector, right? So this is, say, our velocity vector in frame A. In addition, we have this torque term here. So torque, hopefully you recall from statics, So torque of particle P about point Q in frame A is equal to, again, we use a tau to indicate torque, and then this is P about point Q, and that is equal to, again, we have this position vector QP cross with our force acting upon point P. So if we look at our picture above, again, we have this, our position vector here, but imagine force is acting, say, in this direction on particle P, so this would be FP. So you can already start to see the similarities between these two equations for torque and angular momentum. Here we're considering the, in torque we're crossing our position vector with our force vector, and for angular momentum we're crossing that position vector with our linear momentum term. So now that we've defined what the terms torque and angular momentum are, let's return back to our relationship here. First, I just want to say that the derivation of this relationship is presented in the weekly notes, so I highly encourage you to go ahead and take a look at that. The other thing I want to emphasize is a key difference between this relationship here and that with the relationship we learned last week between force and torque. So again, if I write out that relationship, so force is equal to the time derivative of linear momentum, point P in frame A. And so it should become quite obvious that if you were to compare these two relationships, that in the angular momentum torque equation, we have this extra term here. Now, sometimes this term will go to 0, but there are times where it does not. And so it's key that you remember this here. And so just to review some times when it will disappear. So the disappearing conditions. Well, you can imagine that when the velocity of point Q is equal to 0, that this multiplication, or vector multiplication essentially, will go to 0. When you have the two vectors parallel to one another, you will also, their product will also be 0. So when, oops, just write this way. When these vectors are parallel, so in other words, when these vectors, specifically the two velocity vectors, are parallel to one another. And lastly, we have also a condition where Q is actually just equal to point P, right? And so these are just some of the conditions in which this term will disappear. But again, just to emphasize, there are times when it does not. And so just remember that that's a key difference between the two relationships. And so next what we're going to do is, in the following videos, go through how to actually use this torque angular momentum relationship in order to generate equations of motion.